All of you, all there on the other side. I'm DS Hani. I'm working in wireless communication. Okay, just to tell you about myself, I did my BTech long back, 1998 from Aurangabad. Then I did my MTech from IIT Roorkee, 2001. Then I did my PhD from JP University in year 2008. When I did my PhD, then my area was 3G that time. So since then, there are so many students working with me. Till now, I have finished 5 PhD students who have completed PhD with me. Most of them, they worked in the areas of wireless communication like OFDM, MIMO OFDM, wireless sensor networks, etc. And right now, there are 2 students who are still working with me. Many more are there in the queue. So today, my topic is going to be OFDM, Orthogonal Frequency Division Multiplexing. If you are aware of this, I know the audience is including engineering colleges and polytechnic colleges. So I have made my presentation. So in OFDM, if you are aware of this, it's the Orthogonal Frequency Division Multiplexing. So here, today all 4G and beyond technologies mostly are having this OFDM concept. To start with, what is the meaning of OFDM? Since 3G, in fact up to 2G wireless communication, there was not a major problem of fading kind in any wireless communication. The main reason was in 2G and before that 1G, etc. all the data rates are below maybe 10 kbps or 15 kbps at the max. The things like GSM or IS-95, CDMA, they were very easy to work on. But as the requirement of user increases, day by day, number of people are too many, the number of applications are too many. So people move to 3G and beyond applications. Even up to 3G, it was not a very huge requirement of data rates. The upper limit was only up to 2 Mbps at that time. But right now we are working somewhere close to 4G and 5G. 4G is well implemented these days and 5G is about to be there in coming years. So OFDM is a technique which is used these days in all 4G method because the problem of fading is going to be avoided. One of the main technology which avoids fading is OFDM. So to start with here, the concept of OFDM is that we first break the data into small portion. Normally what happens, 4G speeds are around maybe 100 Mbps. And if you see 100 Mbps corresponding time, it is in terms of 10 nanoseconds. To start a bit of duration 10 nanoseconds is extremely difficult. The reason is that we have in wireless communication problems like fading, etc. So those fadings or multipath propagation or delay spread, they all are significant if we start sending bits at very high speed. So that's why it is not recommended to send these bits as it is. So what is done in OFDM, we convert this high data rate high speed data into many parallel number of streams which are having speed significantly less, like we were having 2G. So for example, if we have 10 Mbps data, if I convert that into 100 parallel streams, then each of the stream can be having data rate of 1 Mbps. So to handle 1 Mbps, it is comparatively easier compared to handling 100 Mbps. So that is the reason why we use OFDM, as I said. So as it is written here, we use a number of parallel orthogonal subcarriers to transmit data. Okay, just we'll explain it further in next slide. For example, if you see the bottom of the slide here, OFDM is a concept which comes under multi-carrier communication, and to differentiate multi-carrier communication with the single carrier communication, you can see this slide here. In the single carrier, like our traditional communication, AM, FM, or even 2G or some 3G methods, they are all single carrier communication techniques. So one carrier is used to send all the data. But on the other hand, in the multi-carrier communication, as I said earlier, we divide the coming data into many parallel streams. Each of the stream is having data rate very less, and to each of the stream we give different carriers, either sine wave or cosine wave, and all the different streams, they modulate different carriers, and one of the property of these carriers is that they have to be orthogonal to each other. Yeah, the definition of orthogonality is going to be discussed subsequently. So by doing so, why we go for orthogonality here? Because the very basic reason of orthogonality is that if we send two signals which are orthogonal to each other, they are going to be treated independently at the receiver end. That is property with all orthogonal signals. So we can go for sinusoidal orthogonal signals or cosine orthogonal signals, or typically we can also consider complex exponential signals. Any of the three can be used for orthogonal signals. So that's why we in OFDM we use multi-carrier communication, because the problem of all high data rate is solved there. Now this slide gives you a bit of OFDM and why OFDM is different than FDM. We could have used FDM also. If you see FDM, what are its applications? FDM is also a technology where if we have n number of people, we need n number of bandwidths. But if you recall FDM, then there we need for n number of people, large set of bandwidth is required. And also in addition, between two successive bandwidths or signals, we should have guardband also. That's why OFDM, although it's a good to have, it also provides diversity, but it is not as efficient as OFDM, which is explained in the same slide. So in OFDM, if you can see here, it is possible that multiple carriers, they can overlap. This overlapping condition is only feasible as far as these subcarriers are orthogonal to each other. If you see the shapes of all the signals here, they are just kind of sync signals. And how we get sync here, it is just a Fourier transform of rectangular signal. Because whenever we send a data in digital communication or wireless communication, it is just a digital bit stream. So it's a digital bit stream, and if you see its Fourier transform, it is a sync signal. So only positive part of sync signal is shown here, and most of the OFDM, whenever we discuss it or we do the analysis on OFDM, mostly it is done on Fourier transform or F domain. That's why the signal also, the waveform here shown is also in the F domain. So if you compare these two waveforms, clearly we have edge for this OFDM. In the same specified spectrum, we could place, you can see here, six different bandwidth signals. But on the other hand, in FDM, we could only have two there. That is one of the benefit. It's not the only benefit. The other additional benefit, as I told you earlier, is that it also, one of the reasons to have OFDM is also that it reduces fading problem also, which is going to be discussed subsequently. Then how to pick the spacing between two subcarriers in time domain or F domain, that is going to be a part of our discussion right through this presentation. So now last couple of slides we conclude that why we use OFDM. It's one reason is that it is having higher spectral efficiency compared to FDM. Another is that it is having lower multipath propagation. So multipath propagation is always a problem for wireless communication, but it was not that significant up to 2G because we were having very less data rate. Less data rate, longer bit. So delay can be easily placed in initial part of the bit. That's why it was not a big issue in 2G and below that. So these are two major benefits of using OFDM. This slide also further tells you how OFDM is better than FDM. So 6 different signals have been shown which correspond to 6 different bits in FDM or 6 different users. But if you see OFDM, all the 6 waveforms have been placed almost in half the amount, half the bandwidth. So a lot of saving of bandwidth is there in OFDM. So it seems simple though, but one issue here is all the time there in OFDM, that these subcarriers which have been shown here, they have to be perfectly aligned with respect to each other so that their orthogonality is maintained. If their orthogonality is not maintained, then even small change in subcarrier, it might lead to problem of ICI, which stands for intercarrier interference. Okay, so this is also associated slide to previous one, if you can see. So the first figure is showing multi-carrier. There 6 set of signals are shown. The next is single carrier technique. Third is OFDM. So if you see here, OFDM is not the only multi-carrier method, but it is better than all other 2 methods which have been shown. So let me tell you multi-carrier methods. Other multi-carrier methods are including MCCDMA also. MCCDMA stands for multi-carrier co-division multiple access. We also have that technology parallelly going with OFDM. That technology also has its own issues, but that can be used depending upon our receiver complexity or channel condition, etc. So ultimately, on this slide, it appears that OFDM comes out to be better than all other 2, multi-carrier as well as single carrier methods. Now, this slide also further explains OFDM versus multi-carrier. As I said, OFDM is not the only multi-carrier technique. Okay, so OFDM is one of the multi-carrier modulation method, and in OFDM, sub-carrier spectrum is overlapping. That's a benefit compared to FDMA. In FDMA, if we recall, bandpass filter separates each transmission, which we do not require here, at least as far as orthogonality is maintained. And in OFDM, each subcarrier is separated by DFT. Now, this term which comes first time here, DFT, we'll see here, it is possible to implement OFDM with DFT, and finally, ultimately, instead of DFT, we can also go for FFT, discrete Fourier transform or fast Fourier transform. So, discrete Fourier transform is for discrete signals. So, normally we have signal in the time domain, continuous time domain, but if we sample the signal, it becomes discrete time. For all discrete time signals, we have DFT representation possible. And for DFTs, it is also given in the literature. The DFT can also be implemented using FFT, which is fast Fourier transform. Because we have these days FFT chips available, which can be used at the transmitter and receiver end. So one of the reasons why OFDM was so successful is that we have FFT chips available, and they are quite cheap. They can be easily implemented in our mobile sets or any wireless devices. It do not add cost that much. That's why OFDM is so popular. So everywhere these days we use OFDM, we are bound to use FFT. Not Fourier transform, not DFT, but FFT only. Because it is very cost effective also, and it is approximately resembling DFT. Then OFDM can be baseband as well as passband. Okay. If it is baseband, we need not to have any modulation at all. But if it is passband, we should have modulation also, and 2 categories of modulation are normally used in OFDM. One is PSK, other is QAM, quadrature amplitude modulation. Now this slide shows a typical block diagram of OFDM system. It is a simplified one because there are a few components which are hidden right now. It's not research-oriented block diagram, but it is a simple block diagram. If you can see here, in the beginning, we have coming bits here. So many bits are coming, but as I told you earlier also, the data rate of these bits can be very large. So for example, we can have data rate of 10 Mbps if we go for internet application instead of voice communication. So this very high data rate has to be converted into low bit streams. That is always the concept of OFDM. So that's why in this figure, the very first block is serial to parallel converter. So the coming bit stream is divided into parallel bit streams, and parallel bit streams have significantly less number of significantly less speed compared to the coming data. Let's say, as I discussed earlier, if the coming data is at 100 Mbps, if I divide it into 100 parallel streams, each stream is having data rate now 1 Mbps. So it is 100 times lesser than what it is at the beginning of the transmission. So that is the very first block. Then this signal is typically known to be narrowband signal because the speed here is less than what is, but it is there at the input. All these narrowband signals are given to then quadrature amplitude modulation. Now why QM here? If you see the whole block diagram here, okay, then it is only showing you the baseband OFDM. Nowhere in the figure you are given carrier here. Okay, that's why it is called as baseband OFDM system. So in QM here, all the 100, as I said, just use the figure 100. All the 100 coming bit streams, they are given to QM modulator. Again, the output of the QM modulator is typically points. Okay, this is again a point of discussion that why we need points at the output of QM encoder. If you see a block just adjacent to the QM encoder, it's a IFFT block. IFFT it's just like inverse Fourier transform. Okay, inverse Fourier transform, its discretized version is inverse discrete Fourier transform, then ultimately practically it is IFFT. And whenever we use IFFT, then IFFT needs discrete inputs and it produces discrete outputs. That's why the input of the IFFT block is always needing discrete input signals in F domain. But our signal in the beginning is only in the time domain. So just to convert from time into F domain, we need this QM encoder. If you recall QM encoder, if you are aware of it, it takes the bit stream, convert that into sinusoidal signals. And if you see the constellation diagram of QM modulator, then it just represents points. And those points are given to IFFT block. That's why I told in the beginning, this IFFT block needs point in the beginning. But all the points are in F domain or K domain, because in IFFT we use K domain. So these points are given to IFFT block, then at the output we got signal kind of XN. There's all signal and system issues which are there discussed there. So it's not a big deal. It's very well known to people who are already having BTech background, etc. So at the output of IFFT block, we have XN signal. Then comes next important component which is unique to OFDM, which is a yellow block shown here, which is showing add cyclic prefix. Remember in OFDM I told in the beginning also, it is good idea to work in F domain instead of time domain. So F domain, when we go in F domain, the analysis of the whole signal is comparatively easy. And what the cyclic prefix does here, so anyway that is going to be discussed later, but just I am explaining in one line that cyclic prefix converts a linear convolution which is normally there in all LTI systems into cyclic convolution. And if we do that, Fourier transformation implementation is very easy. So that is there. Then all these parallel streams are added once again. It is converted serially. Then there is D2A converter and the signal is sent. So it is a baseband of OFDM because there is no modulation as such. The QM which is shown in the beginning, that QM is only for individual subcarrier. It's not for overall modulation. So corresponding to all this equipment at the receiver end, we have reverse equipment. If channel is fine, there is not any delay spread kind of problem, we are going to receive the signal accurately. So The next few slides will be explaining all these blocks one by one. So to start with OFDM carriers or OFDM subcarriers. Right now, right from the beginning, we keep on saying that we use so many carriers, so many subcarriers which are orthogonal to each other. This figure shows you 6 different waveforms. Okay, 6 different waveforms are there, and they are all are orthogonal to each other for one symbol period, capital T. Okay, so let's say, to explain it further, let's say in the input of the transmitter, we have a signal whose data rate is 6T. Okay, we divide that data rate into 6 parallel streams. Each of the stream is having data rate capital T. So each of the stream has to be multiplied by one orthogonal carrier. So these are those orthogonal carriers, 6 orthogonal carriers, because we have 6 different streams there. In the figure we have shown only cosine waves. We would have taken it sine wave also, exponential, complex exponential also. So just randomly we picked here cosine wave. So if you see, the very first wave from the top is a cos wave with frequency, let's say f0. Here f0, once again, how to choose f0 now? The frequency of very first subcarrier. This f0 is equal to inverse of the symbol period, capital T. So I told you in the beginning that we divide 6T data which is coming at the input into 6 streams of T speed each. So that's why the symbol OFDM symbol is having duration capital T, and related to that symbol duration is our very first subcarrier f0. So f0 is equal to 1 by capital T. So it is 1 by capital T, and all subsequent subcarriers has to be integral multiple of this 1 by T. So if I take 1 by T as f0, then subsequent subcarriers has to be 2f0, 3f0, etc. Normally, the number of subcarriers chosen is always a power of 2. Okay, like 2 raised to power 6, which comes out to be 64. OFDM is a very common thing. We have 64 OFDM or 128 OFDM, or even 2 raised to power 10, which is 1024 OFDM representation. So as you keep on increasing the value of this 2 raised to power n factor, then the benefits are more and more, but obviously complexity also increases as you increase the size of the FFT or DFT. So the 6 signals all are orthogonal to each other. Now this slide gives you mathematically what is the meaning of orthogonality. Okay, it's for related to the previous slide here. There we were having 2 cos signals, one with frequency, let's say mf0, other with the frequency, let's say nf0. So 2 cosine waves are orthogonal only if they satisfies this condition. When m is equal to n, then this integral for one period capital T, it gives you non-zero result. That answer comes out to be capital T by 2 here. But when m is not equal to n, then the answer has to be 0. So this orthogonality condition has to be maintained. Then only IFFT works. Okay, because OFDM, as I told you, it's dependent upon subcarriers which are orthogonal. They are orthogonal only through this condition. Similarly, exponentials also you can have similar conditions. Sines also have similar condition. Okay, so this condition has to be met. One of the reasons why this condition sometimes do not meet is that because of ICI, which is our inter-carrier interference. Let's say one of the devices from transmitter or receiver is moving. One of the devices is moving, then Doppler spread comes into the picture. Whenever there is a Doppler spread, then carrier frequency changes, and accordingly MF0 and NF0, they are not orthogonal to each other. That's why sometimes we have inter-carrier interference. So this problem, which is also called a synchronization problem, is must. the requirement is must in case of OFDM, which is not as significant in OFDM, FDM, because there we can have adjacent filters also, but here the orthogonality has to be maintained. To reduce ICI, the carriers has to be perfectly orthogonal to each other. Now this slide is further related to the previous slide. Okay, I told you that we have used only cosine waves, but we are not. Let's say if you go back to this particular diagram here, the second block was QAM, quadrature amplitude modulation. Whatever is coming at the input of this device, okay, it is given to two quadrature carriers, sine and cosine. Okay, then if it is given there, then we have two variables, one corresponding to cosine wave, other corresponding to sine wave. So instead of only having one variable an, we have two variables an and bn, where n stands for a particular symbol. Accordingly, you see here, overall signal at any of the stream at the input of the QAM block looks like this. Okay, an cos 2 pi n f naught minus bn sin 2 pi n f naught. Should I continue? Yes. So this if you solve this mathematically, it comes out to be under root an square plus bn square cos 2 pi n f naught plus phi n. So this is the expression which is there at the output of the QAM modulator before IF50 block. Okay, so the amplitude are dependent upon an and bn, and an and bn can take different values depending upon whether you go for 4 QAM or 8 QAM or 16 QAM. So if you go for 16 QAM, for example, an and bn has to be varied in such a fashion that we have 16 possible values. So that is anyway subsequently explained in one of the slides. Now this is how an and bn are calculated from the given signal as BT, okay, signal at the input of the transmission. Okay. Now, previous to this, whatever we have shown, that was all happening at the transmitter end. Okay, so we are doing all this processing, and we started with the fact that if channel is fine, there is not too much fading, there is not too much delay spread, we should be able to demodulate the signal at the receiver end. This slide shows how the demodulation is done. If we assume that the signal which is sent at the transmitter end is SPT, this signal goes to the channel. If channel is fine, then the demodulation procedure is this one showing in this slide, in the second line here. And you can clearly see here that the given signal, this formula actually just reflects that the coming signal SPT is multiplied first by cos signal, then it is integrated. And these two function, multiplication by cos signal, then integration, this is called as correlator. So at the receiver, we are just using correlators. Depending upon the number of streams we are having, if we have capital N number of streams there at the transmitter end, same set of correlators we require at the receiver ends. Okay, so as you can see in the integration, there are small n varies from 0 to n minus 1. There are capital N number of correlators there. So this way the decoding is easy. The decoding is easy only right now because we do not have any impact of multipath propagation or fading, which is going to be contradicted also in future slides, which I'll explain. So till now, whatever I've given, we should be aware of now. Overall OFDM, what it does, it converts a higher data stream into many lower data streams. Each of the stream individually is multiplied by carrier, which is orthogonal to other carriers. Why we do that? Because we want the data orthogonal. Then we combine all These all are combined using a block serial to parallel converter. Then we get the output, then that has to be given to IFT block. Okay, the output of IFT block is again kind of discrete or digital signal. Okay, if you pass this digital or discrete signal through D2A converter, you get baseband OFDM symbol, which is possible to transmit now. Okay, this was all the things which are required for baseband OFDM. Now next is passband OFDM. Okay, everything else stays same for passband OFDM, but we have additional carrier now, because if we want to use OFDM for multiple people, then each of the individual person has to be modulated on a different carrier. Okay, so ultimately the multiplexing is possible only if we use different carrier for different people. Okay, just to recall the things, when we did serial to parallel conversion, it was only for one user. A high data speed of one user is converted into many data streams of the same user, which is ultimately combined. So then given to IFT at the output of the IFT block, data is still corresponding to one user. But when you really want to have multiple access kind of thing, then you have to have multiple users. If you want to use multiple users, then we need modulation there. So that's why in passband we need different carriers for different users. So if you see overall, there are two kinds of modulation happening. One is around the input only, where we use QM, but that QM is not the up conversion. That QM is only to facilitate all the 64 orthogonal subcarriers. It has different roles just to convert time domain signal to frequency domain signal so that IFT is possible. But the passband OFDM, which I am going to discuss right now, is that where we use one carrier which is for all the streams. And because of this passband communication only, the problem which I told you earlier, ICI, appears, because we send this up converted signal to the receiver end, and let's say if the receiver is moving or transmitter is moving, then one of the frequency might change, or the speed of user change, ultimately frequency changes, then ICI appears, orthogonality get disturbed, and there is a problem in reception in that case. So that is there in passband. Anyway, all practical conditions or practical scenarios, many of them are passband working, where we have two modulation, one QM at the beginning, other is up conversion. So we have mostly passband OFDM signal in wireless communication. Now comes the spectrum of OFDM signal. Okay, just to recall, if you have one bit rectangular pulse kind, its Fourier transform is sync signal. Okay, and if you modulate the same rect pulse on any sine wave for a specified period capital T, answer is again sync. But the center frequency of sync is FC now, carrier frequency, instead of F naught, instead of 0. Okay, so normal rect has Fourier transform sync centered at 0. So modulated rect has again a waveform sync, but centered at frequency F, where F is 1 by T. T is a symbol duration. Okay, this figure shows you 5 different streams. They all have different carriers. Maybe if you consider the center frequency FC plus KF naught, then on the right side it becomes K plus 1, then it is K plus 2, on the left side K minus 1, etc. So 5 different waveforms are shown in F domain here. Right? In the time domain we added 5 signals, one under the other. When we go into F domain, okay, on the time they all are same, but in the frequency they have different carriers. FC here represent carrier frequency, F naught here represent 1 by T, where T is the OFDM symbol time, K is integer, okay, which varies from 0 to capital N minus 1, where capital N are the total number of subcarriers. So typical OFDM spectrum looks like this. Okay, and if you see here, it has both positive components as well as negative components. But if you take mod of this, if you consider this whole signal as HF, then HF mod, everything is positive, and if you want to convert power, it is HF mod square kind. Then that also once again, it again is a kind of sync only. Appearance wise, it looks kind of sync only, and there is no negative component in that. So this is what is OFDM power spectrum. As I told you just now, everything is positive. It is still kind of HF only. If HF mod you take and HF mod square you take, shape hardly differs. So this is a spectrum of overall OFDM signal. Okay, it's NF domain. But one thing here has to be understood is that we have used IFT block in the beginning of transmission. Okay, and IFT always needs points at the input of IFT block. But here it's not points, it's a waveform. So this whole signal has to be kind of sampled. Instead of x j omega, we need signal kind of xk. Okay, x j omega is a Fourier transform. Xk is x j omega is a Fourier transform. Xk is discrete Fourier transform or fast Fourier transform. Both are, I'm treating both the same because one is mathematical, other is practical. So the signal has to be converted into xk kind. That's why it has to be sampled. So later on, many of the slides I have shown just sampled version of this F domain signal. Okay, anyway, power at the output of IFT block is kind of this only. Okay, it's the sum of many sync square signals, right? This has to be received as it is at the receiver end if there is no problem in channel. But we'll see when fading occurs, this waveform which is sent, it is also disturbed. Now just to explain what we have learned till now, I'm just showing one example to you. Okay, in the example, there's a digital data is given here in the form of bit stream. Okay. I divided this bit stream into 4 parallel bit streams. Okay, so whatever is the data rate that at the input of the transmission, it is given to serial to parallel converter. There are 4 parallel bit streams. Speed of each is 1/4 of the speed of the input. So those streams are named as C1, C2, C3, C4. So the first step, serial to parallel conversion, is this. Then, depending upon this, okay, if you pick, let's say, the very first signal, C1. In C1 we have, in combination of C1, C2, C3, C4, we have total, if you see here, 24 bits here. Okay, 24 bits are there, and in under one head, C1, there are 6 bits. Out of those 6 bits, first 3 are 1. Next year -1. If you see this slide next now, we have accordingly plotted this signal. For C1, the first 3 bits were 1, 1, 1. Accordingly, there are three cycles of that. Okay, 1, 1, 1, then -1, -1, -1. Digital waveform is multiplied by orthogonal carrier. So in this signal, the frequency or subcarrier frequency of C1 is, let's say, F0. Now come to signal C2. If you just go back to the previous slide, C2 is this 1, 1, -1, 1, 1, -1. So here the green line reflects 1, 1, -1, 1, 1, -1. Then we again multiply this by a carrier. But the carrier we have used here is having double the frequency was used for C1. So it is just a modulation in both the signals, but one with the carrier frequency, not carrier frequency, one with the subcarrier F0, other with the subcarrier 2F0. Similarly, is for C3, the carrier frequency is 3F0. For C4, it is 4F0. It is still orthogonal, all the 4 signal. Okay, it has been shown in F domain now, and all the signals, they are orthogonal to each other because we have chosen sinusoidal signals accordingly. Once again, it is a simplified block diagram explaining what I have given till now. So this figure shows you transmission of mth signal, mth OFDM signal. Okay, if you see at the input, there are total capital NC minus 1 number of bits coming in the mth signal, small m. Okay, so capital NC number of bits are there at the input, and we divide these capital NC number of bits into parallel NC number of bits. Then we multiplied each of the bit by carrier. Here, instead of showing sinusoidal carrier, we have used complex exponential carriers. So the very first bit from the top, A0M, okay, 0 represents 0th bit of mth symbol. It is multiplied by carrier frequency F0. Then next symbol is multiplied by carrier frequency F1, where F1 is equal to 2F0. Then A2 will be multiplied by F2, where F2 is equal to 2F0. This way, we have done this. Then they form finally all are added. So this middle portion is just kind of I50 block. Then it is transmitted through the channel. Okay, then once again at the receiver, if you reach there, which I had given earlier also, you have capital NC number of correlators, then integrator, then this is how the detection is possible. It is just a summary of what I have given till now. Now, I skipped this because some of this I have already explained earlier also. It is telling you how the detection is possible at the receiver, and just to go back, this is the receiver. At the receiver, the very last signal at the end right side, A0M, A0, A1M kind of, it has two possibilities. The one possibility is that the output is AK, or other possibility is 0. Output is AK only whenever the coming signal is multiplied by the same subcarrier. And output is 0 if the coming signal is not multiplied by the same carrier, it is multiplied by different carrier. So this also seems to be explained in other slide. Now if you see overall, when you see the computer simulation, the typical OFDM spectrum looks like this. Okay, so it is just a combination of, it is just like this signal which I have shown you here. This signal was the ideal signal which should be there on the computer when the channel is perfect. There is no fading or multipath propagation problem, right? But practically there is some problem and your signal is like this. But it can be easily detected at the output because fading seems to be not that significant. Now comes the multipath channel. I'll tell you that what is the impact of multipath channel or delay spread on normal communication. The figure shows that there are 3 paths from transmitter to receiver. Okay, and transmitter is fixed here, base station, and the receiver is moving. The person is sitting in the car, person is moving. So right now, at any particular time, the person is receiving 3 different components. One is direct path or line of sight path with amplitude alpha naught and delay tau naught. Okay. Then similarly, first reflected path is through building with alpha 1 tau 1 parameter, next from one of the tree or from the forest with diffraction and scatter and things. Diffraction, having diffraction as well as scattering there, and the amplitude is alpha k and the delay is tau k. At the receiver end, if you see, there are 3 copies of the same signal, one after the other. So just, we have shown it in the next slide. If you see, the channel looks like this now. There is one component at tau 0. Okay, the left side figure where 3 vertical lines are shown. The channel is like this. There are three signals now, one coming at tau 0, other coming at tau 1, third coming at tau 2. Okay, if channel is that way, then our signal which is received at the receiver end, it appears to be there in the right side. We send sine wave, the dark black one is through line of sight, then the first dotted signal is through the building, then third path is through the forest. Okay, so you can see that second and third signal, third waveform enter into the next symbol. Now this is where the problem of multipath is significant. Okay, because second and third waveform enter into the second symbol and they are going to affect the beginning of the next symbol. If we do not do anything to reduce this, then this is going to be damaging our next signal, next symbol, OFDM symbol. So that's why the block which I gave in the beginning, cyclic prefix, has been used in all OFDM. So, okay, if there are more and more multipaths there, the number of reflections are more and more, and number of replicas at the receiver end are more and more accordingly. So one way to tackle this is, which has to be shown in the next slide, you will see. So what we do here, we just copy some part from the, if you see here, we add a gap called TCP. Okay, CP stands for cyclic prefix. So small gap has been added in the beginning of the symbol. And when the first symbol, the very first component of the first symbol reaches at the receiver, then the second part of CP starts again. Now what we get the benefit out of this, that is explained further. You see here, what is done here, we have picked the last, for example, 1/4 portion of the very first symbol, and we pasted that in the beginning at the prefix end of the symbol, which is shown here in the violet color. So this is what is prefix, cyclic prefix, because the name, why this name appears this way, cyclic prefix, because whatever is the last 1/4, around 1/4 or 1/8 portion, depending upon how bad channel is, we pick some portion of the symbol from the back, put it in the beginning. Okay, so why we do that? Because all the reflections from various paths should be absorbed in that violet region. Okay, if we are able to do that, then our next symbol is not going to be disturbed because of our present symbol. Okay, that's why cyclic prefix is must. One of the other option which can be used, we need this small TCP kind of gap always. So instead of TCP, we can also have a blank period also, or some other, which you call zero padding. Zero padding also is possible there, but gap has to be there. Why we maintain those gap, that gap? Because in this small gap, all the reflection has to be fit. Okay, depending upon the delay spread, we choose this particular gap. So this gap is always there. But as I told you earlier, we have two options. One is cyclic prefix. We can take some part from the back, paste in the beginning. Okay, that is cyclic prefix. Or we can just maintain small gap in the beginning. Both are the possibility. But why we go for cyclic prefix in OFDM? Okay, the preferred choice compared to zero padding is cyclic prefix. Why it is so? Because when you use cyclic prefix, then the normal linear convolution of LTI system is converted into circular convolution. And the implementation of circular convolution in DFT is very easy compared to linear convolution. Because in OFDM, most of the analysis is done in F domain. So that is the reason why we use the cyclic prefix, because the implementation of FFT is easy and F domain analysis is easy. Otherwise, zero padding also is one of the options. If you don't want to put cost of cyclic prefix, you can go for zero padding. Okay, but still, in all the OFDM applications, we will use cyclic prefix because it gives us benefit of linear to circular convolution. So the same is explained in this slide once again. If you see, if we have the very first rectangle from the bottom side is CP. Okay, you have useful symbol. We have taken some part of the first useful symbol. We have copied it and pasted in the beginning. Okay, so that we convert linear convolution to cyclic convolution. Then same is done in the second symbol also. Same is done in the third symbol also. But we have to make sure we do not take CP very large, because more is the width of cyclic prefix, more is the overhead which has to be sent along with the data to the receiver end. And if you send more overhead to the receiver, then transmission capacity decreases. So then transmission capacity decreases for that. So this is the reason why we should not have. So CP is always a compromise. If we use very small CP, then there might be a delay spread problem. If we use too much CP, then there might be capacity reduction problem. So there has to be a trade-off between the two. Now, till now, all previous slides, we have assumed that our channel was smooth. Channel was smooth because the delay spread was not too much. We have flat fading kind of problem. But moment we go for fading, which is frequency selective fading. Okay, we are not explaining here right now that how this frequency selective fading affect single carrier communication. That is a well-known thing. All single carrier communication are very much affected by fading, with frequency selective fading. Okay, but now in this figure we'll see that even if it is frequency selective fading, OFDM can somehow reduce this frequency selective fading, which is not possible to reduce in single carrier communication. As shown here, our red signal, a red line is showing the impulse response of the channel in F domain. And the blue signal is just the spectrum of OFDM signal. Okay, when the signal comes, it is passed through the channel. Okay, okay, then signal shown in red color is the impulse response to the channel in F domain. Okay, it is not flat like we have in the flat fading channel. So this variation in HF shows that it is a frequency selective channel. When this frequency selective channel is multiplied by the signal OFDM symbol spectrum, overall result appears to be there on the right side. If you see here, each of the individual subcarrier is not affected that much. Okay, so it is very easy to decode the signal at the receiver end. Okay, in single carrier communication, we have how we tackle this frequency selective fading. We are supposed to use equalizer of quite a big length, which is always complicated issue and costly issue. But in case of OFDM, because frequency selectivity is reduced significantly, we can use equalizer, but a 1-bit equalizer or 2-bit equalizer at the max is sufficient for OFDM. Or sometimes we do not require equalizer at all. So that's why this slide gives you the major benefit of OFDM, that OFDM is well suited for frequency selective channels. Okay, because individual bit stream after serial to parallel conversion is a narrowband signal compared to wideband signal at the beginning. And if you have a narrowband signal, then for them frequency selectivity is automatically very less compared to wideband signals. Okay, that's why in 2G systems or 2.5G system, fading was less because they were kind of narrowband signals. And the spectrum, whenever there is we have frequency selectivity, the spectrum also changes a bit. This is a typical computer simulation model which shows you the frequency selectivity in the spectrum of the signal. Now, let's now come to a very small addition to what we have learned till now. Okay, because the major issue is always channel, right? So channel estimation always is a problem in any wireless communication when we send high-speed data. So till now, all the subcarriers we have shown in FFT IFT block were using data subcarriers. All the subcarriers for data only. But practically, we know that the channel is sometimes time varying. Okay, because other transmitting modes. Sometimes when fading issue, channel estimation has to be done frequently, and whenever we do channel estimation, we need pilot symbols. Okay, that's why this slide tells you the pilot symbol has to be added in the normal data symbols. If you see here, figure on the left side. Okay, now as I told you earlier, it's not typical time domain. It's not typical Fourier transform waveform. It is a discretized version of Fourier transform where we have shown samples. All the vertical lines are corresponding to different subcarrier here on the left side. If you see here, the blue one, whose strength is shown to be more than the strength of black subcarriers, they all represent pilots. And the pilots are placed uniformly after some data subcarriers. And the role of these pilots is for channel estimation. How many pilots has to be added, that depends upon how complex the channel estimation problem is. If channel is highly time varying, then we need to add more and more number of pilot carriers. If channel is kind of flat only, we need not to have too many pilot carriers. Few set of pilot carriers are sufficient. Okay, so here along with the data subcarriers, pilot carriers are also added. So if in the IFFT block at the transmitter end, we have, let's say, 50 subcarriers. Then out of those 10 subcarriers can be used for pilots, remaining 40 for data. Although it can never be 50 subcarriers in IFT, because one of the conditions for IFT FFT block is that the number of inputs and number of outputs has to be of the order of 2 raised to power n. Okay, one of the applications which I'll explain later is 802.11 LAN, where the number of subcarriers are 64. So there's a role of pilot carriers. So pilot carriers are inserted in between the data subcarriers, and the number of pilot carriers depends upon how bad the channel is. So this is one thing which has to be done in that block. Pilots are sent frequently, and number of pilots used is also a time varying factor. If channel is highly time varying, we use more pilot carriers. If channel is not time varying, we use less number of pilot carriers. Then there is one problem in OFDM, which is called peak to average power problem. Okay, if we use as I said you earlier, let's say now we use 100 subcarriers. If we use 100 subcarriers, then 100 parallel streams are there which has to be added before the FT block. And when we add 100 subcarriers, then it might happen that each of the subcarrier, let's say it's a highly rare scenario though, it's a very rare scenario though, but it might be possible that all the bits, they're 1. And if we add all the bits which are 1, there are 100 such number of streams. Overall amplitude is 100 volts or 100 units. And that's why the amplitude of this sum, when we add so many carriers, this is vary from 0, 1, 2 up to 100. Okay, so the treatment of the signal for 1 volt or 10 volt or 20 volt or 100 volt, it has to be same, which is a very difficult scenario. Normally in single carrier, our amplitude is not going beyond 5 volt or 6 volt or 10 volts. When we add 100 number of signals, then the overall amplitude is 100 times the voltage of the one signal. Okay, the voltage of, let's say the amplitude of one signal is A, the total amplitude can be 100A. So that's why the amplifiers which are used normally in single carrier communication, they fails for OFDM. Okay, so if we want to use OFDM smoothly, then we should have very good amplifier whose dynamic characteristics has to be very wide also. Okay, it should be amplifying 1 volt signal also, 10 volt signal also, 100 volt signal also, which is very rare. Very rare. So because it adds cost to this. Anyway, it's not recommended to have power amplifier or voltage amplifier or that bigger dynamic range. Okay, this slide typically tells that the fluctuation of the spectrum. Okay, when we add it is addition in, it's not spectrum actually, it is a OFDM symbol in time domain. When we have, it is only shown for 8 number of subcarriers. If all the subcarrier data is 1, you can see the top figure here, the amplitude typically might touch 8 volts, although it's rare though. So when it touches 8, and on the other hand, it also might touch sometimes -8. So the overall amplitude variation is -8 to +8, which is 16 volt. So that's why the requirement of power amplifier is having bigger. We should have power amplifier with bigger dynamic range. It is only for 8 subcarrier case, but if let's say we have subcarriers of kind of 1024, then so much dynamic range is required, which is not possible. Okay, so there's always a problem in this OFDM peak to average power problem. Peak power is significantly higher than average power. To avoid this problem, there's so many things which are proposed in the literature. Like one of the thing is just before that, we can see that the power amplifier should have such characteristics, very wide dynamic range. Okay, peak power can be very large, average power is just a moderate one. So that is a problem which is there in the power amplifier. Okay, this has to be avoided. There are different tools how we can avoid peak to average power problem. It is a well discussed problem since many years. There are few options here. We can go for clipping, etc. Whenever amplitude of, let's say, signal goes beyond 10 volts, we clip it. We keep it 10 volts only. Similarly, in the negative direction, when the signal goes beyond -10 in the negative direction, we clip there also. So clipping is one of the options, but it produces distortion. And also there are other alternatives, like we can have good coding techniques also. Forward correction codes can be used there. Scrambling techniques also can be used. So anyway, this peak to average power problem is there, but it can be sorted out. Another is important thing which is required or must in OFDM is OFDM synchronization. OFDM principle is possible only when we have orthogonal subcarriers. Okay, at the transmitter end there is no issue, but when we go to the receiver end, then receiver might be moving. If the receiver is moving, there is Doppler phenomena coming into picture. So overall carrier frequency might be changing. If carrier frequency might change, orthogonality of signals get disturbed. If orthogonality of signals get disturbed, then it's not a good reception. Then the reception occurs there. That's why synchronization has to be maintained. Okay. OFDM, although OFDM systems can handle frequency offsets of up to 2% of delta F, where delta F is inverse of symbol time. Okay, sometimes 5 to 10% also can be tolerated, but if the Doppler spread is too much and person is sitting in a high-speed train or transmitter receiver, both are moving, then Doppler effect is quite significant, and there is very large amount of change in frequency. So this totally disturb orthogonality and the reception becomes wrong in that. So that additional thing has to be maintained in OFDM, which is synchronization. Then choosing OFDM parameters. Okay, one of the important thing is subcarrier spacing. There are consequences that you can't choose subcarrier spacing too much, too high, or too small. Okay, if you choose subcarrier spacing too big, the problem is that we have very large cyclic prefix required there. Okay, and cyclic prefix, large cyclic prefix means we have additional overhead. Transmission capacity reduces. So that is also not recommended. But if you go for very crowded subcarriers with very small spacing, okay, then it increases frequency sensitivity also. Then ICI may be more in that case, because more the spacing between the subcarriers, okay, then ICI can be handled easily. So anyway, there has to be compromise between spacing of subcarriers. Now, before moving to one of the application of OFDM, just now to summarize overall what is happening in OFDM, we split channel into narrowband channels, which enable significant simplification of equalizer design. Okay, as I told you earlier, 1-bit equalizer is sufficient in OFDM compared to a large length equalizer in single carrier communication. Effective implementation possible by FFT. Okay, then these are a few benefits. Then few challenges also, like large peak to average power ratio, number 1. Number 2, synchronization problem is there. Number 3, ICI problem is there. So there are few issues also which are explored since many years. People are exploring this. Some solutions have been found. Okay. So just overall now, whatever I have discussed, I am giving you in this single figure here. The input data stream is coming. It is going to parallel streams, then added cyclic prefix, then power amplifier, then to channel, then ultimately to the receiver where correlator is there, and we are detecting it. Now we'll see the waveform on the same figure to make it better understandable. You see, when we see serial to parallel conversion, there are capital NC number of signals. Each of them before multiplication is a rect signal, and every rect signal is having a Fourier transform which is a sinc kind. And when all these are added, then we get such kind of waveform in F domain. If you see here, so many sinc signals have been combined, overlapped. Okay, and the spacing between two sinc waveforms is 1/t, which is a symbol period, right? Then after that, cyclic prefix is added, then power amplifier, then channel. Channel shown here is frequency selective channel. Okay, so all the sinc waveforms have been multiplied by this frequency selective channel shown in red color. Okay, then output after the channel looks like this, right? So this is without any synchronization or proper channel estimation, because frequency selective is there. We can go for pilot carriers also. Once again, if you see left side, we have added now pilot symbols shown in the blue color, which I explained already. So pilot symbols have been added. The use of pilot symbol, the output at the cyclic prefix is appearing this one here. Now our output is as shown on the right side. It is well synchronized now. Because of this pilot facility, not only channel is well estimated, also synchronization problem has been solved. That's why we have this pilot carriers at the transmitter end. Now let's see one of the application which you are familiar with this already probably. It's a Wi-Fi or 802.11 LAN. 802.11 LAN, which is also called as Wi-Fi, it has so many varieties. Okay, one of the possible variety in that is having OFDM. There are two standards in Wi-Fi called 802.11a and 802.11g. They both use OFDM as a technique, right? 802.11a, for example, works in a band of 5.15 gigahertz to 5.35 gigahertz, as well as 5.725 to 5.825 gigahertz. 8 channels have been used in this. Every channel is having a total bandwidth of 20 megahertz, and we can have 12 channels possible to use in this band. Similarly, 802.11g is working in 2.4 gigahertz band. So we focus on the very first one, 802.11a only. Both use OFDM. Okay, as I told you here in this 5.15 to 5.35 gigahertz and 5.7, etc., you have 12 channels. Those channels are shown here. Okay, each of the channel is having bandwidth 20 megahertz. There is 30 megahertz spacing in the beginning of bands. Okay, 30 megahertz spacing at the end of the bands, and each of the band itself is having bandwidth 20 megahertz. So why this 20 megahertz has been chosen, I'll tell you just now in the subsequent slides. So in 802.11a LAN, in that case, these are the various parameters which are used here. We have total N, capital N is equal to 64 FFT size. I told you already that FFT size is always 2 raised to power n power. Here that small n is equal to 6, that's why 2 raised to power 6 is 64. 64 FFT size is there. Okay, sampling frequency is 20 megahertz. I told you that if you want to use FFT or IFFT block, then the signal at the input has to be sampled one. That sampling rate is 20 megahertz. Cyclic prefix is having capital L is equal to 16 samples there. So if you add both, it becomes 64 plus 16. Total 80 number of samples exist in one OFDM symbol. And the duration of these 64 samples is, you can see here, 3.2 microsecond, and the duration of cyclic prefix is 0.8 microsecond. So this way, one OFDM symbol in 802.11 is having duration of 4 microseconds. Now these all parameters we are fitting in that IFFT block. As I just told you, there are total 64 samples, right? And the sample has to be chosen in such a way that there has to be some provision for pilots also, for data also. Okay, as it is shown here. If the input side, there are total 64 inputs starting from 0 to 63. So 0 is not used, the input 0 is not used, C1 to C26, there are total 26 number of subcarriers there. Then there are few nulls up to 38. Up to 38, that means there are 12 nulls from 26 to 38. Then C minus 26 to C minus 1, again there are 26 number of subcarriers are there. So out of total 64 subcarriers, we use 26 plus 26, 52 subcarriers. So out of 64, we use 52, that means 12 are not used, right? So that's why the small rectangular box on the left side, it is written as NF equal to 52, because out of 64 we use 52 carriers only. Okay, and also there are 4 pilots used out of those 52 number of subcarriers, and the pilots are placed at, if you see at the bottom of the slide, pilots are placed at number -21 pin, number -7, +7, 21. There are 4 pilots used. You know that pilots are used for channel estimation. So it is just same thing which was there in the previous slide. Okay, in F domain or K domain. The total duration is 4 microsecond, 0.8 microsecond for cyclic prefix, where all the delay spread is covered. Total frame size is 4 microsecond. And this is the figure, which is once again, I am putting all the parameters of 80.802.11 into the actual OFDM block. Data comes, it is given to interleaver. Okay, you know what is the role of interleaver. Just data is intentionally randomized so that the burst errors are reduced. That's the role of interleaver in any wireless communication. So in 802.11a also we use interleavers. It's not the part of OFDM though. Okay, but 802.11a uses interleaver. Interleaver is used, then 40. Then these number of bits are 192. Then these are mapped with 16 QAM. So every group of 4 bits is mapped into a 1 QAM symbol. So that's why 192 bits has been converted into 192 by 4, which is 48 number of symbols. Those 48 number of symbols, we have 48 number of symbols which are given to IFD block, right? IFD block along with the 4 pilot symbols. Okay, it is shown here that 48 number of symbols are given directly from the data. 4 number of pilot symbols are added, few nulls are there. Okay, then this is what is happening in the 802.11a LAN. So with that, this was our whole discussion of OFDM. Okay, just considering the audience aren't going into typical research areas of this. Okay, people are working on this. Many research areas are there, and these are a few applications which uses OFDM. Okay, asynchronous or asymmetrical digital subscriber lines, synchronous digital subscriber lines, etc. Wi-Fi, digital audio broadcast, digital video broadcast, WiMAX, Flash OFDM, ultra wideband is also one of the topic these days under research. Power line communication. These are various applications where OFDM is useful. Okay, finished. Yes.
Query.
Yeah, if you are having any query, please you can ask.
Any query from the centers? Any query from the center?
Thank you, sir.
Please.
No query, sir. Thank you very much.
Thank you, sir. Thank you. Welcome.
Evening.
Thanks a lot, all of you. I hope you understood some of it. Bye for now.
Sir, tea मंगवा रही है.
अच्छा.
Hello.
Hello, yes, sir.
कोई query पूछ लिया.
Hello, yes, sir.
Sir, I am from Government Polytechnic, Bid, Maharashtra.
Yes, sir.
Sir, there is a question about the session.
Yes, sir. Yes, sir. Please,
Yes, sir, please,
sir
sir.
is coming.
Yes, sir. बोलिए.
Good morning, sir.
Good morning.
Sir, in multi-channel, multipath channel frequency diversity, how cyclic prefix overcomes the need of complex equalizer?
How cyclic prefix overcome?
The need of complex equalizer.
Yeah, the thing is that normally what happens, equalizer, why we need equalizer when channel is too complicated, right?
Yeah.
And it is for wideband channels. But OFDM, in the beginning only, it converted all the wideband signals into narrowband channels. It is just like a 2G channels now.
Yeah.
Yeah, whenever it is a very small data rate, then equalizers are hardly required at all. Ultimately, equalizer is required for wideband channels.
Yes.
Yeah, this is a simple reason why we don't require equalizers.
Okay, sir. Thank you.
Any other question, sir?
No, sir.
Or any other question from any other center? Fine, sir. Then.
Okay, thanks a lot. I'm here for 1 or 2 minutes more, that's it. Please ask if you have any query.
Okay, thank you, sir.